Hi, this is group number 9. For our EMS627U coursework, we worked on simulating and controlling the Turtlebot 3. Our goal was to take what we learned about kinematics and ROS in the lectures and get it working on the physical hardware in the lab.
Before running any code, we considered the kinematics. The Turtlebot 3 is a differential drive robot. By controlling the velocities of the left and right wheels independently, we generate a linear velocity v and an angular velocity omega. We verified this behavior in simulation first to ensure our method was correct.
We started in the gazebo simulator. We didn't want to risk breaking the real robot, so this was the best place to test. You can see here we're driving around a world filled with obstacles. This confirmed that our velocity commands were being published correctly to the CMDVal topic.
For mapping, we utilize the Gmapping package. As shown in the diagram, the Gmapping node takes the scan data from the LiDAR and the odometry data from the wheel encoders. It uses a particle filter to fuse this information, estimating the robot's pose while simultaneously building the 2D occupancy map. You can see that process happening here in Arvis. The green dots are the live laser scans. As we drove the robot around, it built up the map in real time. The white pixels are free space and the black lines are walls. This confirmed our sensors were calibrated correctly.
See how when we moved it, it's remapped some of it?
Moving to the lab, we faced significant challenges. We initially followed a guide for ROS2, which caused major package conflicts with our required ROS1 noetic setup. This resulted in broken dependencies, forcing us to completely wipe the Raspberry Pi and perform a fresh install of Ubuntu 20.04.
Additionally, we found that the university's Azure Run Wi-Fi blocked the peer-to-peer ports needed for ROS. To solve this, we set up a dedicated Android hotspot to act as a gateway, creating a private network for the PC and robot. Once the network was stable, we verified the connection. On the left, we're running the teleop node on the remote PC. On the right, the robot reacts instantly. The table test was crucial to confirm our ROS master URI configuration was correct before placing it on the floor.
Okay, so that's proof that it's working. Control logic. For the final task, we implemented obstacle avoidance. We initially tested the built-in Turtlebot avoidance node, but we found it was too passive. It simply stopped the robot dead when it saw an object. Phase 1. We improved this by writing our own Python script in Phase 2. As shown here, our logic checks if the LiDAR distance is below 0.5 meters. If it is, it actively commands a turn to the left, allowing the robot to navigate around the object rather than just stopping.
On the screen, you can see the custom script running. We have set up the spray balls as obstacles. On the terminal, the distance there streams in, and when it drops, the script prints obstacle detected and triggers a turn. On the right, the robot drives forward, detects the bottle, and autonomously turns to avoid the collision. Overall, Despite the OS and the networking hurdles, we have met all the coursework goals. We successfully migrated from the simulation to a physical deployment and implemented autonomous reactive control. Thanks for watching.